Okay, epoxides. So I assume when you come to lab tomorrow, Friday, you'll be ready to go, yeah? Okay. Epoxides, important chemistry. You see epoxides in some biological processes. For example, blood clotting. Vitamin K important in blood clotting, and vitamin K is converted to an epoxide in the body during the blood clotting process. Okay, applications, lots of places. Reactions. I think we're here, yeah? The previous page, is that right? Under acidic conditions, we're doing right now, and if there's a tertiary site, we'll go tertiary. If not, we'll do SN1. If not, we'll do SN2. Is that right? Okay, we got an ether. Can we protonate it? I assume you can protonate an oxygen in a mechanism. What's next? What's the nucleophile here? Do we have a tertiary site available? No. So what's going to be the nucleophile? And what's going to be the mechanism? Okay, this is an aqueous acid, so we have water, and water will attack kick that off, and we will get what product? Boom, boom, boom. OH here, and there will be a oxygen here with two H's. Plus, when the nucleophile comes in, okay, and we have to then lose the proton. What can take the proton? Well, what gave up the H plus over here? Bisulfate anion, yeah, can come in and take the proton, leave electrons behind. And the product is there, except it's going to be just deprotonated. Yeah? Plus what? What did we reform? Plus sulfuric acid reformed, okay? So basically the acid is catalyst, right? How we do? How's it look? What type of product did we make here? A what?
A diol.
Yeah, it's a diol. Got two OH groups. It's a dialcohol called a diol. How about the next one? Guys, I see a lot of people, a lot of you working on this. This should have been worked on before class, right? Okay, a little bit late now. Showtime. Is that right? Everybody agree? Let's move on to the next one. Product down here. I'll let you work on that on your own. Okay? We can delay past the quiz if you like. Quiz on Friday. Mechanisms. Important note, opening of epoxides under acidic conditions to yield a carbocation is a very easy and thus common in epoxide mechanisms. This may lead to a simple SN1 substitution, as in some examples above, but once you have a carbocation, a variety of other chemistry can take place, such as what? What a carbocation is prone to doing? Rearranging. What else can you do with carbocations? Instead of substitution, they can lead to elimination, ultimately like an E1. Yeah? Once you get to carbocations, you're doing carbocation chemistry, and okay, don't forget that. Lots of things. Resonance, carbocations, you can show resonance, yeah? Very common. Mechanism below, how do we do on that one? Anybody have any questions about that mechanism? Questions about that mechanism? If not, let's move on to under basic conditions. But I thought ethers were unreactive under basic conditions. That's right, most ethers are. But epoxides are unique, and epoxides will react under basic conditions, largely because of the ring strength. Okay? All right? Now, under basic conditions, the mechanism is always what? SN2. So that's easy, yeah? Because still what apply, it's never going to just ionize and make carbocation without acid. And under basic conditions, there is no acid. So under basic conditions, we're not going to protonate the oxygen and it ionize to make carbocation. No carbocation, because you got to have acid for the oxygen to do that. It's always SN2. Now, what type of nucleophiles can add here? Okay, these are going to be stronger nucleophiles. One common, well, they're all common. One example is an acetylide anion, which comes from removing the H from a terminal alkyne. We've done this in Organic 1. Okay. I think we've already seen it in Organic 2 already, haven't we? I think so, maybe not. Common basis for doing this, sodamid, yeah, or N-butyllithium. Again, sort of seen this already, is that right? Okay, two common bases. This is really a textbook base. That's actually a terrible base in practice because it's not soluble in organic solvents. Because it's very ionic, there's no organic there. And if you put it in water, well, you've destroyed your base because this will just take the proton from water. This is much more soluble because it has the butyl group. It's more soluble in organic solvents. Okay. Traditional acid-base reaction, take the H, leave the electrons behind. You get the acetylide anions, they're called. Sometimes called alkanide anions. Usually called acetylide anions. But these, strong nucleophile, these will come in here, and we're fixing to break a couple of rules. It's okay, because it's epoxides. They're very unique. This will come in here and attack. This is a symmetrical epoxide, the simplest you can have. Okay? So both carbons are the same. The name of this is, let's see if we can get to the name of it. First off, 2 carbons. What's the name of that alkene? It's so simple you can't think of the name, right? What's the name of that alkene? Ethene. Okay? Now with eth, often there's a YL ended. Because it's kind of like the ethyl. But very often instead of ethene, it's called ethylene. Okay? Ethylene. Now what do we call something when we add oxygen to it? Like maybe if you have a nitrogen compound and you add an oxygen to it, you get something like this. Nitrogen oxide. Yes. What if we take ethylene and make the epoxide? Double bond to the epoxide? Which is that? That becomes known as ethylene oxide. There's no O minus, but it has taken on an oxygen. That's commonly known as ethylene oxide. Okay? You take this nucleophile, will come in here and attack the carbon. Again, they're both the same here. And kick off the oxygen. It's like, that's SN2, right? What rule did we break there, though? What are you like? How do you make oxygen a better leaving group? Protonate. Is that oxygen a good leaving group? Not according to those rules, but guess what? Epoxides, it will leave. This is the first time we've ever done this. Did we protonate the oxygen? No, this is under basic conditions. Okay? The oxygen of an epoxide will leave the carbon in an SN2 type reaction. And so we're breaking that big rule. Why? Largely because of ring strain. Okay? What does that arrow movement give? Well, isn't the alkyne carbon bonding to the carbon here? We made that bond, right? Nucleophile bonding to carbon. Oxygen's gone, but then there's another carbon, and the oxygen is going to be bonded to that other carbon, right? When it opens up, you got to see that. Nucleophilic addition to the epoxide in an SN2. It's such an SN2, but it's a little weird because the oxygen goes and protonated again. We get this. That's an anion. Now we can go neutral and supply a proton. There's no proton internally to be there. We got to come in a separate step and add a proton source. Either acid or water will supply it. ACL or sulfuric acid or water. If you throw in water, it will supply a proton. We can put the proton on. Acid might be a little bit better and more common. And we can get a product here. There will be an alcohol. That's nothing to memorize. Yeah, it's an alcohol if you do the mechanism. Okay? Now, very common here, I will say this. This outcome in general is, what was that fragment? What was the R alkyne? What was that in the reaction here? What's that right there? What's that? It's a nucleophile, right? Okay. And then you have 2 other carbons. Where do those come from? The nucleophile is bonded to this one. And when that opens up, the oxygen is bonded to the other one. Nucleophile is bonded to that one. When the oxygen used to be bonded to there, but it opened up, but it's still bonded to the other one. Okay? In the end, this is a statement that we can make to remember this. Nucleophile, these reactions here are giving nucleophile, carbon, carbon, OH. Okay? Nucleophile, carbon, carbon, OH. All right, we'll see that again. So acetylide anions. Another common nucleophile is just alkyl anions. Carbon again, but alkyl carbon, not alkyne carbon. And I feel it. You guys don't feel it yet, but your life is about to change, okay? Okay, see, I know, all right? And in 30 minutes, your life will be very different, okay? All right? All right.
Is it about to get better or worse?
Huh?
So is it about to get better or worse? About to get more complicated?
It will be different. It will be better. Okay, alkyl anions. I mean, up here. Those are readily made because that's SP, it's quite stable, relatively. But what about just an alkyl? You know, like that. Well, if you put a lithium with that, that is into the lithium plus. So that's what we used. That's that right there. That's often used as a base. Okay? Can we use it as a nucleophile? Yeah, we can. But let's introduce this and say some things. Okay? A regular alkyl, which are typically often regular alkyl, trying to remove an H of a regular alkyl like we did up here, okay, it's much more difficult. Easier with the alkyne, more difficult with alkyl. Very difficult unless the R group is SP, like above. A tricky way to do this, a better way to do it, is to actually start with the alkyl halide, like the alkyl bromide. Things we traditionally used as for substitution or what, like with leaving groups. Okay? All right. Now you can come back. This just gives you the full information. But basically, you treat these with some type of metal. And the metal is usually a group 1 metal or a group 2 metal. Okay? Group 1, for example, lithium. That will give us something like this. Group 2, magnesium. Okay? If we look below, so you can see what we're talking about here. If you take an alkyl halide, such as bromide, and treat it with lithium metal, oxidation state is 0. Often you do this in an ether solvent, such as ether or THF. You will get the alkyl lithium. Now, the fate of the Br is Br minus and lithium bromide, so 2 lithiums, so this actually takes 2 equivalents of lithium metal if you want to balance that, see that. This is actually a redox reaction. Now I'm showing this covalent. Often they're shown covalent. Coming out of Gen Chem, you should say, well, that should be ionic, because group 1 is always ionic. If you show this as ionic, you would show this as minus and lithium plus, which is what I showed over here. So that's 3 carbons and this was 4, because N-butyl lithium is most common. But you can make N-propyl lithium as well. And so this here is essentially, the anion. Mechanism, I'll mention it down here. If you use magnesium, it will react. First off, before we go there, let me speak mechanistically. What's going on here is what's redox. The lithium is metal, it's 0. The lithium is now what? Well, if you consider it ionic, you can see what it is. It's now +1. So it went from 0 to +1, so the lithium has been oxidized. Okay? And we say the alkyl halide has been reduced. But it's a redox reaction. You see, you've got redox going on. Since the metal is being oxidized, this is called an oxidative addition. Okay? It's most likely a radical reaction. We're not going to look at precise mechanism. But essentially, the metal inserts between the carbon and halogen. Now, with lithium, the halogen ends up being kind of cleaved and they give a separate molecule. But you can see that with magnesium. The magnesium sort of inserts between the carbon and bromine. It's called oxidative addition. It's often shown covalent. If we show this fully ionic, which magnesium coming out of Gen Chem, you should say, shouldn't that always be 2+? And I'd say, okay, we'll do that. We showed it like that, it would be minus. Magnesium 2+. And then Br what? Minus. If you want to show all that ionically, it would be like that. And you see the magnesium metal went to magnesium 2+. The magnesium got oxidized. Something got reduced. But again, these reagents are known to have a lot of covalent character. The bonding is sort of between covalent and ionic. I know in Gen Chem you said it's either ionic or covalent, right? It actually can be sort of in between. Okay? It can be a very polar covalent approaching ionic. Okay? But they're often shown like this. You can consider them the ionic. If you consider them ionic, what do you really have here? You see? They're both what? They're both that, which is what we're after. And so we didn't make this by removing an H. Okay? Removing an H, very difficult. Instead, we did this sort of tricky oxidative addition chemistry using a metal, and we started with an alkyl halide. Okay? Now, the lithium is commonly done, but what I was referring to changing your life is the Grignard reagents. Okay? Because this is super common in organic chemistry, and today you have officially been introduced to Grignard reagents. Very good nucleophiles used in lots of chemistry, including epoxide chemistry, and when we get to carbonyl chemistry, we'll see Grignards over and over. Okay? Grignards are essentially alkyl or carbon anions. You can theoretically do this with many metals. The very first metal to ever do this is shown to do this, I think, was zinc. Back in like the 1850s, somebody treated an alkyl halide with zinc metal, and they discovered this. They got some chemistry going on, and it was doing an oxidative addition and making this. So the metal will react here. Yes.
How is it that the magnesium gets in between the...
What's the mechanism?
Yeah.
Okay. Again, I said it was probably a radical reaction. Okay, a single electron transfer radical reaction. That we're not going to look at a mechanism. Okay? But what's driving this? These metals over there don't mind giving up electrons and becoming positive. That's the chemistry they do. Hey, I want to give up an electron. Well, Br likes to become what? Minus. And so ultimately the magnesium became positive, Br became minus, and that's kind of the driving force. This gives up electrons, and how does it come in here? Well, you can look up that in advanced text. Probably not going to see mechanism for this in your introductory textbook, but it's called an oxidative addition. Palladium will do this, and the 2010 Nobel Prize in Chemistry went to general chemistry involving palladium. And it's a very complex mechanism, but the first step of that is oxidative addition of the palladium between the carbon and halogen. Okay? It's chemistry that can take place. Sometimes the mechanisms are not defined well, but chemists have been doing this and recognized this for 150 years. Okay? The first metal was zinc. Zinc is a metal, but if you take an alkyl halide and heat it with the zinc will actually dissolve. Because it's metal, this tends to be soluble, all that tends to be soluble. Even though it's ions, well, it's, again, it has lots of covalent character. It tends to be soluble in ether solids. Okay? Which again implies that it's got some covalent character. Because if it was all just ions, it probably wouldn't be soluble in diethyl ether.
So I was wondering what our ultimate goal is is it just to create a good, strong nucleophile?
Yes,
is that what we're doing that? Okay.
Yeah, it's to create these, but we're creating them not by removing an H,
Okay.
like we did up there.
Right.
Like you might traditionally do this.
Okay.
We're not, that's the thing. We're not using a traditional acid-base mechanism. We're using an oxidative addition of a metal.
Right. To make
More of a tricky way to essentially to make these.
that then can just be reactive with other stuff.
Now it can be used as a nucleophile, just like we did above. Question?
So isn't group 2 metals only have one equivalent, so would you never see it like with magnesium with 2 equivalents?
Theoretically, you can get an outcome different from shown. With magnesium, usually you see it with one halide remaining. Depending on your stoichiometry, you can get products that have composition sort of like 2 alkyl groups on the magnesium. And this is magnesium plus, 2 plus, and then a minus carbon, so it's 2 minuses. And but usually you do stoichiometry to leave with 1 halogen. Because these things don't react quite as well. The dicarbon compound doesn't react quite as well as the monocarbon. So usually you do the stoichiometry. And since magnesium is 2 plus, you can have 2 minuses. See, lithium, since it's plus, can only have 1 minus. And if that's minus, you're like, well, what's the fate of the Br minus? Well, the Br minus sits with another lithium, and the only way to have 2 lithiums is to have 2 here. Okay? And again, we're not doing full mechanism to see all that. But, yes. With group 2, and magnesium is the most common. The lithium and magnesium are the most common. You can theoretically do it with many metals. And of these 2, magnesium is super common, and it gets its own name, and it's called the Grignard reagent, Grignard reaction. Alkyl lithiums may be called the Gilman reagent, but that you never see that. I think that's probably not in your book. But Grignard's certainly there. Okay? Okay, ether solvents are very good for Grignards. They're commonly used. Okay, now we can do chemistry here. I think Grignard won a Nobel Prize back in like 1905. Right at the turn of the century, late 1800s, 1896, 1898. He's the one who discovered that magnesium would do this. Or at least was the one who early on did work that I think he discovered. But 40 years before he came along, it was known that zinc would do it, and probably a few other metals. But he's the one that really showed that magnesium would do it. And it's something about the magnesium products. They tend to be very usable. Stable enough that they can be used and then make things. And he really showed the versatility of them. And 100 years ago, it became the big thing to do in chemistry is use a Grignard reagent. It allowed for making new compounds, lots of new stuff, because again, a neutral carbon is not a good nucleophile because it doesn't have a lone pair. And again, making these anions by an acid-base reaction is quite difficult. And so the Grignard approach really made things easier. The ingenuity, creativity, discovering what Mother Nature will do when these chemicals are combined. Okay, first reaction. What's lithium going to do to this over here? It's going to make the alkyl lithium. Okay? So this is going to give... And we can show these any way you want. If you want to show them ionic, that's fine. Usually when you see a Grignard, it's going to just be showed MgBr or MgI or something. But you can use it as if it's ionic. Everybody agree that lithium is going to convert it to the alkyl lithium? You got this anion? Okay. Now if we come in here with the epoxide, we got a nucleophile. Which carbon? Now this is not a symmetrical epoxide. Which carbon are we going to attack? Left or right? Right, correct. Why? Because we're doing SN2, always with strong nucleophile, and we attack the least sterically injured side, correct? And what does this give? There's the two carbons of the epoxide. No change in stereochemistry there. Oxygen just opens up. Yeah? It left this carbon, just opened up. What's now on this carbon? The nucleophile, which is 3 carbons. Okay? 1, 2, 3. Which bond did we just make? Bond there, right? But look at it. We're making a carbon-carbon bond. Part of this long chain, we connected it up there. Carbon-carbon. Now, appropriate workup, what's that going to do? What's the purpose of workup? Protonate the oxygen. Remember, previous page, it's a separate step. It's got the H has to come from somewhere else. There's no H internally. Okay? What kind of workup do you want to add? What do you want to do here? Add what? Add what? Add water or your favorite acid. Okay? Add H2O or ACl or something. All right? Instead of redrawing this, can I just do something? I mean, it becomes OH, right? Or do we need to redraw it? Okay. OH. 1, 2, 3, 4. 1, 2, 3. Yeah? Okay. I'm not going to do this but once. Okay? Yeah, I mean, if you add in some ACl, this is going to do that and give you that product, right? What type of product did we make here? Nucleophile, carbon, carbon, OH. What was a nucleophile? Wasn't it 3 carbons? Nucleophile, carbon, carbon, OH. Now there may be something else on the 2 carbons. Okay? Nucleophile, carbon, carbon, OH. These reactions with epoxides will always give that. Okay? Back here, when this is minus, there's always got to be a positive. What would be the positive sitting with this? That would be lithium, right? Okay, let me show the product of the one below.
I have a question real quick.
Uh-huh.
Would the lithium also pair up with the Cl minus after the oxygen takes hydrogen?
What do you think?
It would, right?
I mean, if you want to show it at the end, yeah. At the very end, you're going to have lithium fluoride. Your ions are always there. There's always going to be a positive and a negative to balance. I mean, if there's a cation, you got to have an anion. If the cation ever disappears, it would only happen because of redox. I mean, lithium plus could go back to lithium metal. That's only going to happen with electricity, though. But originally, the lithium metal went to lithium plus. But if you're going to show it as plus, then you would show the Br as minus. Okay, anybody got a product for the next one? What's step 1 going to give? Step 1 is going to give phenyl magnesium iodide, right? Benzene ring phenyl. And this is essentially what? What's the business part of this?
Your phenyl?
Phenyl anion, okay? You can just sort of draw that like that. That's kind of condensed. Let's draw it out more completely. One of these carbons is an anion. Now this is an sp2 carbanion. But you can also do Grignards with aromatic rings like this. Okay? Very common. And then this attacks oxide, opens it up. Which carbon? Left or right? Right there, you're at. Open it up. And that's going to give, can I go ahead and include the proton step? Instead of having to draw the minus and then protonate it. That's going to give what? We're going to have here, oxygen opens up. We got that there. Got that there. Got that there. We got a benzene ring, I'll just say phenyl. And the oxygen minus, though, this is like the second step that I'm saying happened, it's the third. And this becomes OH, right?
Do we change the orientation though of our first methyl that's coming off there on the left next to your phenyl? Will you end up pushing that back?
You get inversion.
Okay, so it is
Inversion here,
inverted.
right?
Okay,
We got inversion.
Okay.
I showed inversion.
okay.
Why would we push the methyl back?
It is inverted, that's what I was just thinking, it doesn't look inverted initially to me, but I didn't work out the RNS, so that's what
Well, okay, but how is it inverted?
Well, I guess does it just
What's
push it
going
up
on here
or-
is the methyl is forward.
Uh-huh,
Okay, here we go, let's do it. The methyl's forward like my elbow's forward towards you. The leaving group, the oxygen is how? Forward, back, what is the oxygen?
it's going up, right?
Straight up, okay? Like this. The pencil's going straight up,
So it just pushes that
okay?
back
The
instead.
methyl's going forward,
Right,
oxygen's going straight. Since the oxygen's going straight up, how does the benzene ring anion come in?
from the bottom.
Straight down. It comes in straight down, and it's going to kick the oxygen off.
And your elbows.
But now the phenol's down. But what happens to the methyl?
It
it just
pushes
does this.
instead of-
It makes
okay,
room.
That's right,
But it's still forward,
yeah,
okay?
uh-huh,
But it's inverted. The umbrella's like this, and then it went like that. It is inverted.
okay,
But see, the leaving group is straight up. The nucleophile I drew straight down. The methyl moved up.
okay,
I know how to do that. We've done it a couple of times.
yeah.
It is inverted because, well, if you can do RNS, it's a little more complicated. You can do RNS. So. It shouldn't be that complicated because there's only one thing here. What's high priority on this carbon? Oxygen is 1. What's next? Carbon, all these carbons would be 2. Methyl would be 3. Undrawn H in the back is 4.
So it's R,
That's R.
that'll be 1, 2.
This should be S as long as the phenyl is a high priority group, just like the leaving group was. And indeed it is. This is 1. You can look at the ring. It's a benzene ring connected to that carbon. That's 2. That's 3. H is in the back on here. And so it's 1, 2, 3. What is this?
S,
S.
okay.
It is inverted. Look back at the handout I gave you in organic 1, where we talked about 2 ways to make nucleophile carbon bonds. How do you add to a cation both ways? The other way is backside attack, and I showed you 4 or 5 different ways to see this. And this is one of the ways. Leaving group straight up, nucleophile straight down. Now I drew it over here, but I could have drawn that phenyl just straight down. I mean, just twisting a little bit is still down in the plane. Okay? There you go. And of course it is, what was this in the reaction? Nucleophile. Nucleophile, carbon, carbon, OH. Everybody agree? Well, we got some stereochemistry there. Next reaction here. How about that epoxide with ammonia? Ammonia is an sp3 nitrogen. It can be considered a strong nucleophile. Okay, it's neutral. So let's see what the outcome here is. Which carbon is it going to attack, top or bottom? Bottom, right? Less sterically hindered, kick off the oxygen. What does that give? Okay, nitrogen's bonded to this carbon, but it's going to be, look, leaving group is forward. Off of that carbon, the oxygen is forward. It's also connected up in there, but this carbon, the oxygen is forward. See, the bonds here, the oxygen is at both forward. It's sticking out this way. It's forward. So how does the nucleophile come in? If the leaving group is forward, the nucleophile comes in from the back. So the nitrogen is going to be like this. And that is a nitrogen, but how many H's here? 3. We don't just magically lose H's. Okay? I lost it here, but I indicated there was a step there that I just wasn't showing because I didn't want to take the time to waste ink, etc. You know how to, okay. Positive, right? What's up here? Well, there's no change in stereochemistry up here. The methyl is back, and the oxygen is forward. It's just no longer bonded down here. But the oxygen is what charge? Well, it's all in your mechanism. It takes on a third lone pair, and it's now minus So that's the first intermediate. Now in this case, we don't have to have any appropriate workup because there's a proton source here. We generated a proton source. The nitrogen wants to act as an acid and let something take the H. Well, the oxygen is very willing to take it. You could do internal. That's possible, but instead I'm going to do something more generic. And we're going to do this 100,000 times as we move along. Remember how I said we got to take care of the proton? This is an example of taking care of the proton. We generate sort of this. This we're going to get a final product. Oh, it's not aromatic. The O minus picks up an H, becomes neutral. Where did it get the H from? Got it from the nitrogen. And there's your final product. I'm not going to show mechanism. What's commonly shown here is just to say H plus transfer. Okay? H plus transfer. And you got to know that there's going to be a lone pair here. Okay, it's an acid base. Yeah, it may be internal, but most often as we move forward, it's often intermolecular. Because in your flask, you have 1 billion of these, and they're all swimming next to each other. Well, guess what? The oxygen, I'll just cut that off. That's the second molecule. The oxygen of another molecule will come in here and take the H, leave, okay, traditional acid base, that's where the lone pair comes from. Another molecule. But guess what this can be interacting with? The H of another molecule, and I'll just cut that off. Okay, all these molecules are next to each other. So this molecule takes an H from the nitrogen of another molecule. And you leave the electrons behind. But all this is going on, okay? We've got 1 billion molecules in the flask. And so instead of showing all this, we often just say H plus transfer, and you have to understand what that means. Basically, a proton, an acidic proton was generated here, and that needs a proton. Okay? Now from now on, I'm just going to say H plus transfer. And we'll do it 1 million times. And when you get to biochemistry, you'll do it all day. But in biochemistry, they'll never explain what happened. And if you don't know, then you'll be lost. Okay? You'll be like, where did the H go? And you have to just be confident and say, okay, I know what's going on here. Okay? We're taking care of the proton, H plus transfer, et cetera, et cetera. All right? There you go. Now, this could have been just shown as NH2, right? I drew full structure. Okay. But what do we got? Nucleophile, carbon OH. Yeah, anybody agree? So here the amine was a nucleophile, and it generated, we had to go neutral. We didn't have to have an external workup. We generated a acidic proton. Okay. Proton transfer there. There's some below. Some below. Do the other two below on your own. We'll look at those. Quiz on Friday. Okay. It may include some epoxide chemistry up to where we've come. It may include alcohol oxidation we covered in lab. Okay, basically everything we've covered. Okay, alcohol reactions, ether reactions, including epoxide. All right. There won't be any tomorrow on the quiz. but we need to start moving on NMR. We'll do some of that on Friday.